let's talk a little bit then about some calculations that we can actually do using the periodic table. And so we've already talked about the idea of atomic mass, the fact that the periodic table gives us an average atomic mass that we can calculate from isotopic abundances if we just kind of know how much of each one's present. But we can use that same kind of logic to figure out molecular masses, where all we need to do is, if I know the chemical formula of the substance, I can just add together the atomic masses of all of the atoms that make up the molecule and kind of take it from there. And so, from that perspective, then, if I know the molecular formula, all I need to do is just look up what the masses of each of the atoms are. So take, for example, ammonia here. Ammonia, NH3, has one nitrogen atom and three hydrogen atoms. So if I take the mass of the nitrogen atom, which is this 14.07, and I take the mass of three hydrogen atoms, each one being 1.008, then the end result is I get these together, and the overall mass of the molecule would be 17.09 AMUs. Now, the same thing can be done for ionic compounds as well. Now, technically speaking, ionic compounds don't form molecules. Their arrangements are a little bit more complex than that, because you've basically got this large array of ions that are all alternating in this large crystal. And so we tend to call those formula units. And so the technical term, instead of molecular mass, would be formula mass. But same kind of principle applies. I've got the molar mass of calcium, which is 40.08. And the molar mass of chlorine, which is 35.453. And there are two of them because there are two in the formula. And so if I take that and add two of those to it, I get 110.984 as the atomic mass for the formula unit of calcium chloride. Now, this is all well and good, assuming that we are actually dealing with individual molecules or individual formula units. Problem is, that's rarely what we're actually doing. And so what we have to do is we have to start to look at things from a broader perspective. If we're doing any kind of chemical reaction, if we're doing any kind of work in our laboratory, we have to understand, okay, there's a problem with our setup. I'm not going to be able to measure individual molecules. And so this is where a mole comes in. Now remember, mole is one of our base units in the SI system. And the mole stands in for this number, Avogadro's number, 6.022 times 10 to the 23rd particles, or formula units, or molecules, or atoms, or whatever the case may be. Now, the number here is derived. We are working off of the assumption, and again, I've made this case before, I'll say it again. Every single unit starts with some definition somewhere. And so the definition for the mole and the definition for AMU have the same origin. That is, it is that many atoms in exactly 12 grams of carbon-12. Remember, our AMU was defined by 12 grams of carbon-12, or 12 AMUs of carbon-12, being the definition for a molecule. Well, now 12 grams of carbon-12 is being the definition for a mole. And so 1 mole is that many particles. So there are Avogadro's number, 6.022 times 10 to the 23rd atoms in 12 grams of carbon-12. There are 6.022 times 10 to the 23rd atoms of carbon-12 in 1 mole of carbon-12. And so every other determination of the number of molecules, every other mass is based off of those determinations. But one of the really great things about using this conversion is by converting things into moles, we now have a consistent way of comparing one set of objects to another. Because if I have 1 mole of carbon and 1 mole of nitrogen, I know that those two samples have the same number of atoms, have the same number of molecules or formula units. If I can get it down to moles, I know I can compare them directly. Whereas if I'm comparing masses, 100 grams of iron is going to have a much different perspective than 100 grams of hydrogen. 100 grams of iron is only going to be a little less than 2 moles. 100 grams of hydrogen is going to be almost 50 moles. And so the number of particles that I get in the one sample versus the other are vastly different. And that's going to play a considerable role in how we determine how much each of those substances can react in different chemical reactions. So we use the mole as kind of this key conversion point where we can compare the amounts of things available in our chemical reactions directly. Whereas grams are easy to weigh. It's an easy unit to measure, but it's not considerably accurate in terms of how many particles we're actually dealing with. Whereas moles gives us that number. And so from that perspective, then, we can use Avogadro's number as a means to compare the number of particles of something and the number of moles of something by simply using Avogadro's number as a conversion factor, just like we did in chapter 1 with using conversion factors to go from grams to pounds or liters to milliliters or anything like that. So let's take a look and do a quick practice problem. If I have a sample of 2.59 times 10 to the 18th formula units of calcium chloride, how many moles are present? Well, to do this problem, I'm going to need to take that starting material, 2.59 times 10 to the 18th. And actually, for simplicity's sake, I'm going to use scientific notation here, the kind that your calculator gives. So capital letter E is going to stand in for this 10 to the negative 18, or 10 to the, or times 10 to the part. Okay. Now I'm going to do that conversion. One mole of calcium chloride is equivalent to 6.022 times 10 to the 23rd formula units of calcium chloride. And so we can see that my formula units cancel out. I'm left with just moles. I bring out my calculator, 2.59 times 10 to the 18th divided by 6.022 times 10 to the 23rd. And I get 4.30 times 10 to the negative sixth. And that is moles of calcium chloride. Okay. One quick but really important note. If you do not know how to use the exponent button, this is not showing up the way it should wanted to. If you don't know how to use the exponent button on your calculator, hit me up. I will try to help you as best as I can. If you have a TI model, it's going to show up as an EE in one of your secondary functions. If you have a Casio like I do, it's going to be the EXP button, which is this one right here. But what that does is that saves you from having to type in times 10 to the caret, saves you from having to put in all the extra parentheses and whatever, because if you don't do this step, if you make a mistake, like say you forget a parenthesis or you put it in incorrectly, what happens is it'll interpret this as 2.59 times 10 to the negative 8 or 10 to the 18th divided by 6.022 times 10 to the 23rd, and you'll end up getting some sort of number times 10 to the 40th. So if you're not familiar with how to use your calculator to do scientific notation, let me know. I'll try to walk you through it separately here, at least as best as I can with what I have to offer. But it's really important that you know how to use your calculator, especially for these kinds of functions. Scientific notation can be brutal on your calculations and lead you to quite a few incorrect answers if you don't treat it properly. So if you have questions about that, please let me know, and I'll try to give you some more individualized help in a later session. But for right now, let's go and move on to talking about molar mass. Now, molar masses take that idea of the mole, take that definition of Avogadro's number and the 12 grams of carbon-12, and apply it thusly by basically saying that I don't need to do any manipulation to the periodic table values. The definition of Avogadro's number, the definition of an AMU, basically cause the Avogadro's number and the AMU conversion to grams to cancel out. So the number of AMUs that an individual atom has is the same as the number of grams an individual has if we're talking about moles. So the way that we calculated molecular masses or atomic masses or formula masses is the same. The only difference is instead of talking about things in AMUs, we're going to talk about them now in grams. So just as an example, an atom of helium, according to the periodic table, weighs 4.003 AMUs. A mole of helium weighs 4.003 grams. And so that is its molar mass, 4.003 grams per mole. And so what this allows us to do, and I like these kinds of visualizations, by the way. You're going to see a number of different kinds of visualization maps from me throughout the course of the rest of this semester. And the reason I like these is it's very easy to kind of follow to figure out what I need to do. And so I use these often as roadmaps, tools to help me to go between one substance and another, or to help me figure out how to frame my calculations so that I end up with the right substance or the right calculation in the end. And it works something like this. Let's imagine for a second that I needed to calculate the mass of a compound based upon the number of atoms of a particular element. So let's say I want to go from, you know, number of carbon atoms to grams of carbon dioxide. Well, the approach that I would end up taking is that I would need to start here with my atoms. I would need to go up and calculate the number of moles of carbon that I had. I would use the chemical formula to go from moles of carbon to moles of carbon dioxide. And then I'd use the molar mass of carbon dioxide to figure out its total mass. And so if I follow along here, I can see that my first step would be to take atoms and divide by Avogadro's number to figure out the number of moles. I'd use the chemical formula to say, okay, every carbon dioxide has one carbon in it. And then I'd use the molar mass of carbon dioxide to convert from the moles to the grams. So I could do this from a number of different perspectives and a number of different starting points. All I needed to do is this basically just helps me to organize my calculations moving forward. So this is a really powerful tool, and we're going to see it used in a number of different cases along the way here, especially when we get into the more calculation-driven chapters, like chapters 7, 8, 10, 11, and so on. Let's start off with some practice problems, and then we'll take a short break. So how many moles of ammonia gas are present in 24.92 grams of ammonia? Now, if I go back to I have a mass of ammonia, and I'm trying to convert it into moles. So I know to do that, I'm going to need to divide by the molar mass. And so really the only thing that I need to do to solve this particular problem is I need to find the molar mass. So molar mass of ammonia, ammonia is NH3. And so I have 14.01 grams per mole for nitrogen. I have 3 times 1.01 grams per mole for the hydrogen. So my total mass is going to be 17.04 grams per mole of ammonia. Now, using that map on the previous page, we can either just simply divide this, or if we take the more dimensional analysis type approach, 24.92 grams of ammonia and using that molar mass as a conversion factor now, 17.04 grams in 1 mole And so now I can see my grams are going to cancel. 24.92 divided by 17.04. I get 1.462. .462 moles of ammonia. And so that's really all that there is to this particular type of example. Any questions?
Nope.
No.
No.
Okay. And so let's take a break then. Let's come back in about 10 minutes. So let's say about 10 after 10, go ahead and get up and stretch and move around. And we'll come back in a few minutes.
All right, sounds good.
Okay, so we're back. Now before we move on to the last one here, the last bit, we're going to look at, let's just do one more practice problem that's a little bit more involved, a little bit closer to what you would see on the homework. And it's a question like this: how many nitrogen atoms are in 85.11 grams of dinitrogen pentoxide? Now, again, the way to kind of focus this, the way to organize this would be to go back here and look at, okay, I'm starting with a massive compound. And I want to take it all the way to atoms of an element. So there are a couple of steps that I have to go in. And so the way I can look at it is that each one of these line segments represents an individual calculation that I'm going to have to do. So I'm going to need to do a conversion or a calculation to go from mass of compound to moles. I'm going to have to do a calculation to go from moles of compound to moles of element. I'm going to have to do a calculation or a conversion to go from moles to atoms. Now, since all of these are essentially conversions, the easiest way to go about doing this would be using dimensional analysis. So taking that Q, if I start with my 85.11 grams of dinitrogen pentoxide, my first step would be to convert the grams of this substance into moles. Now, the way to do that is with a molar mass. Molar mass of dinitrogen pentoxide, mass of nitrogen is 14.01, and there are two of them, so 1401 times 2, plus oxygen. Oxygen is 16.00 times 5. I get 108.02. .02 grams for every mole of dinitrogen pentoxide. So my grams have now canceled. I'm left with moles. Now the second conversion here, I want to go from moles of dinitrogen pentoxide to moles of just straight up nitrogen. For that, that's where the chemical formula comes in. I know that for every one of these, I am going to get 2 nitrogens. And so my moles cancel out. I'm left now with just moles of nitrogen. And then the last step, I want to go from moles of nitrogen to atoms of nitrogen. And this is where the Avogadro number comes in. 1 mole is 6.022 times 10 to the 23rd. And so my moles of nitrogen cancel. And now I do my calculation. 85.11 times 2 times Avogadro's number divided by 108.02 is to 4 significant figures. $9.490 times 10 to the 23rd atoms of nitrogen. And so this is probably about as complex as these kinds of problems can get. But again, if you kind of follow the roadmap that we were put on, in this problem, you can see we've done each of the steps along the way. We started with our mass. We used that mass and the molar mass to convert it into moles. We used the chemical formula to turn the moles of the compound into moles of the element. And then we used Avogadro's number to convert that moles of element into atoms. So every step along the way corresponded to one of these calculation steps that we did in the dimensional analysis. So it was all done intentionally. It was all done quite purposefully along the way. And so if you're not sure what the next step is to follow, kind of keep that in mind. Keep in mind that you've got these things in place that'll allow you to do these steps in particular, and allow you to kind of organize yourself to make sure that you're doing the correct calculation steps. All right. Any questions or thoughts before we move on?
Yeah, no.